So 12.9 or 12.69 asks us why steam at 100 degrees Celsius burns worse than liquid water at 100 degrees Celsius. So the severity of a burn is going to depend on how much kinetic energy the sample transfers to your body, right? So you've got your arm here, and your skin is at a certain temperature that's healthy and allows your skin cells to survive and thrive. And that's because the skin cells there on your arm are made up of molecules that are vibrating around, but not too much, right? So your cells are constructed in a way, there's a cell membrane and all the parts on the inside of the cell are functioning. If you give your cells too much kinetic energy, in the individual molecules, the lipid molecules and the carbohydrate molecules inside your cells and the DNA and proteins that are in there, if they start moving too fast, then they'll start to break up because they'll be colliding with the other molecules around them so hard. The bonds, covalent bonds and intermolecular attractions that hold those molecules together properly won't be strong enough to hold them together if the collisions are too strong. And so we're going to talk more about that a little bit today, where if you put too much energy into a substance and the molecules start to collide, the collisions are so strong that the attractions holding the electrons in the molecules and atoms no longer are strong enough to hold them together. The collisions cause them to break apart, and that causes a burn, right? So the idea here is if we can transfer more kinetic energy to these molecules, it will be a more severe burn because the molecules will be moving even faster, and the faster moving molecules will break up more due to the stronger collisions that they experience. So ultimately this question comes down to which can transfer more kinetic energy to your skin, steam at 100 degrees or water at 100 degrees? Well, you maybe are thinking that they should be the same because 100 degrees Celsius is a high temperature, so that means it's a high kinetic energy. And so that means the water, whether it's in the liquid form or whether it's in the gas form, whether it's steam or liquid, those water molecules come down at a high speed because they have a lot of kinetic energy, and they create strong collisions between themselves and the molecules that make up your arm, and that causes the molecules in your arm to start moving really fast, and that can break up their bonds. Right? So it's basically like the water molecules are acting like little explosives or little bombs. They're coming in there and smashing into the surface of the other molecules. That breaks up the other molecules because there's too much force in that collision. So if the liquid and the gas are at the same temperature, they should be transferring, on average, the same amount of kinetic energy to the arm. So why is it significant if one is in the gas phase and one is in the liquid phase? Right? Right. So the difference between the gas and the liquid is in the liquid, the molecules do have some hydrogen bonds. Right? So big partial negative, big partial positive attraction there. Whereas in the gas phase, the molecules are far apart enough where in the steam, most of the molecules are not forming any attraction. So why does that matter? If they're at the same temperature, they have the same amount of kinetic energy and the same amount of average motion. So it's not really correct to say that the gas molecules have more motion, because you might be able to say that the gas molecules have more translational motion, because if they're not holding it together with any attractions, they do express their motion more translationally, meaning that their motion is the type of motion where they're just kind of flying through space. And the liquid might have more vibrating, stretching of the bonds. The molecules might be vibrating more. But vibrational motion and translational motion are both forms of motion, and they both can transfer that kinetic energy to your arm and cause a burn, with equal efficacy. So the key thing here is, for the water that's going to come in here and you're going to land on your arm, if that hot water gets on your arm, the only kind of energy it has to transfer to your arm is kinetic energy. So some of the kinetic energy in the water, because it's at a high temperature, gets converted to kinetic energy in your arm because it's at a low temperature through collision, right? So water molecules in the liquid are moving fast, whether it's vibrating, rotating, or translating. That higher temperature, faster moving molecules, when it hits your arm, they start colliding with the molecules on your arm, and your molecules in your arm start to move fast, and they start to break up, and that causes a burn. When the gas comes in, it does the same thing. Right, so if this gas comes down and hovers over your arm, it does the same thing. It transfers kinetic energy from the gas to kinetic energy in your arm. But it also transfers some of its energy in addition to that due to the intermolecular attractions that form. So if I've got this steam where the molecules are translating too much to attract one another, and these molecules come in contact with your arm, the arm will slow down the water molecules and they will condense, and I will form liquid water on their arm. And that will form some attractions between the partial negatives and partial positives of the water molecule. So the liquid already has hydrogen bond attraction. The only type of energy you can transfer to your arm and burn your arm with is the kinetic energy that it has. The gas molecules have the same amount of kinetic energy because they're at the same temperature. So when they land, they can also transfer the same amount of kinetic energy to your arm that the liquid water does. But in addition to that, when they land and form attractions, the forming of attractions is a phase change. So that corresponds with a decrease in potential energy, and that potential energy is converted into the form of kinetic energy. So anytime, what we talked about last time was, anytime you form attractions, the molecules become more stable. So the water molecules in the gas start to condense on your arm into a liquid. That condensation process is forming hydrogen bonds between the water molecules. Those are some attractions. That will cause the water molecule to become more stable, lower in potential energy. So when I go from the high potential energy gas where they don't form attractions to the lower potential energy liquid water on the surface of your arm that's forming attractions, that formation of attractions is a decrease in potential energy. So I don't have space here, so I'll just circle this and go up here. I've got a decrease in potential energy. So that potential energy is converted into kinetic energy. So there's extra energy, extra kinetic energy that goes into your arm in this scenario, because some of it goes into your arm just because the gas is at a higher temperature and it transfers that kinetic energy through collision. But more goes into your arm because the gas molecules are forming attractions, which means their potential energy is going down, and that energy is converted into the form of kinetic energy, which goes into the surroundings, which is your arm. So your arm's absorbing more kinetic energy overall in that scenario than when just the liquid touches your arm.